Welcome back to Cosmic Drift, where every point of light in the night sky is a story waiting to be told, a mystery waiting to be decoded. In our previous journeys, we have marveled at interstellar visitors, travelers from the stars. We have seen their familiarity, their strangeness, and their diversity. But one question still lingers, a question of origin. Where did they come from? What were the homes they left behind like? Tonight we will not just observe a traveler. We will become cosmic archaeologists. We will follow the footprints of 3I Atlas back through time across the vast interstellar ocean to find the place it once called home. A lost home, under the light of a red sun. This is a journey into a hypothetical world, a world reconstructed from the few clues this visitor left behind. Let us begin the investigation. Every investigation begins with evidence. So what were the traces that led scientists to the prime suspect of a red dwarf system? The first and most important clue lies in the very path 3I Atlas took. When astronomers discovered it, they didn't just calculate its future trajectory as it departed. They could also do the opposite, rewind the film. Using extremely complex computer simulations, they input all the observed data, its position, speed, and direction of travel. Then they reversed the gravitational effects of the sun and the planets. They pushed Atlas back out into space along the exact path it came from. This process is called orbital back integration. It's like watching a film in reverse of a stone being thrown to find the hand that threw it. As they rewound tens of thousands of years, they saw Atlas exit the solar system's sphere of influence and begin its straight journey through interstellar space. And the direction it came from was not random. It came from a region of the sky with no bright stars or special clusters nearby. This ruled out the possibility of it coming from a close neighbor. But more importantly, by comparing its trajectory with the movements of millions of stars in the Milky Way, from the Gaia satellites, data scientists could begin to search for potential encounters in the distant past. Although no single star was identified as the exact culprit, statistical simulations showed that an object with a trajectory like that of Atlas was most likely to have begun its journey from a red dwarf system. Why? Because red dwarfs are the most common type of star. They make up 75% of the stars in our galaxy. In terms of pure probability, a random visitor is far more likely to come from a red dwarf system than from a sun-like system, which is much rarer. It's like meeting a stranger in a global city. Chances are high they come from one of the most populous nations. Red dwarfs are the most populous nations of the Milky Way. The second clue, a more subtle but no less compelling one, lies in its chemical fingerprint. As we explored in our previous journey, the brilliant blue color of Atlas was a cosmic neon sign signaling an unusual abundance of organic carbon compounds. It was a carbon comet. This is not entirely typical. Although comets in our solar system also contain carbon, the explosive activity and brilliant color of Atlas suggested a higher concentration. This implies that the cradle that created it must have had a special chemical environment, one that favored the formation and preservation of complex organic molecules. And this is where the red dwarf hypothesis becomes truly compelling. Red dwarf stars, especially after they have passed their initial flare stage, emit less high-energy ultraviolet radiation than sun-like stars. UV radiation is the very thing that can break apart complex organic molecules. An environment with less UV could act as a better chemical preservative, allowing these molecules to survive and accumulate in the cometary ice at a higher concentration. So, we have two main clues: the trajectory, which suggests a common origin, and the chemistry, which suggests a special formation environment. And both of these clues point in the same direction: a red dwarf system. This is not absolute proof. It is a well-founded inference, a case built on circumstantial evidence. But it is the most robust hypothesis we have, and it is also the most fascinating one, because it allows us to do something extraordinary, to use these few clues to begin a journey of the imagination, a reconstruction of a lost world, a home we will never be able to see. And so the detective's work is done. The explorer's journey is about to begin. Welcome back to Cosmic Drift, where every point of light in the night sky is a story waiting to be told, a mystery waiting to be decoded. In our previous journeys, we have marveled at interstellar visitors, travelers from the stars. We have seen their familiarity, their strangeness, and their diversity. But one question still lingers, a question of origin. Where did they come from? What were the homes they left behind like? Tonight, we will not just observe a traveler. We will become cosmic archaeologists. We will follow the footprints of 3I Atlas back through time across the vast interstellar ocean to find the place it once called home. A lost home, under the light of a red sun. This is a journey into a hypothetical world, a world reconstructed from the few clues this visitor left behind. Let us begin the investigation. Every investigation begins with evidence. So what were the traces that led scientists to the prime suspect of a red dwarf system? The first and most important clue lies in the very path 3I Atlas took. When astronomers discovered it, they didn't just calculate its future trajectory as it departed. They could also do the opposite: rewind the film. Using extremely complex computer simulations, they input all the observed data, its position, speed, and direction of travel. Then they reversed the gravitational effects of the sun and the planets. They pushed Atlas back out into space along the exact path it came from. This process is called orbital back integration. It's like watching a film in reverse of a stone being thrown to find the hand that threw it. As they rewound this film, they saw 3I Atlas moving away from the sun, its speed slowing as it climbed out of our gravity well. It passed the orbits of Jupiter, then Saturn, Uranus, and Neptune. Finally, after rewinding for tens of thousands of years, the simulation showed it exiting the final sphere of influence of the solar system, the Oort cloud, and beginning its nearly straight journey through interstellar space. And the direction it came from was not random. It came from a region of the sky with no bright stars or special clusters nearby. This immediately ruled out the possibility of it coming from a close neighbor like Alpha Centauri. Its journey had to be much longer. The next step in the investigation was an extremely complex task. scientists used data from the European Space Agency's Gaia satellite. Gaia is a cosmic cartographer measuring the positions, distances, and proper motions of over 1 billion stars in the Milky Way with unprecedented accuracy. They took the backward trajectory of Atlas and compared it to the movements of millions of stars in our local neighborhood, also wound back in time. They were searching for a potential encounter in the distant past, a moment when Atlas and a particular star were very close, suggesting it might have been ejected from that star's system. This is an incredibly difficult job, like trying to find 2 grains of sand that were near each other in a sandstorm millions of years ago. The initial simulations found no clear culprit, no single star that Atlas had passed close enough to be certain it came from there. This suggested its journey must have been very long, perhaps hundreds of millions or even billions of years. In that time, the Milky Way itself had rotated many times, and the stars had drifted far apart. The trail had gone cold. However, the investigation did not end there. If one cannot find an individual, scientists can look for a population group. They ran statistical simulations. They created millions of virtual comets from different types of star systems. Sun-like stars, giant stars, red dwarfs, and saw what their trajectories would look like after being ejected upon arrival at our solar system. And the results showed a clear trend. Objects ejected from red dwarf systems due to their orbital characteristics and their common locations in the galaxy were the most likely to enter our solar system with a trajectory like that of Atlas. So the first clue was established. The trajectory did not point to a specific home, but it pointed to the most probable type of home. The trajectory had shown us a direction, a most likely suspect based on statistics. But to strengthen the case, the cosmic detectives needed another type of evidence. Something more physical, a fingerprint. And fortunately, 3i Atlas left a very clear fingerprint written in the language of chemistry and light. That was its brilliant blue color. As we explored in our previous journey, this color was a cosmic neon sign signaling an unusual abundance of organic carbon compounds. It wasn't just a comet, it was a carbon comet. This was the second clue, a more subtle but no less compelling one, a chemical fingerprint pointing to a different formation environment. Let's review the evidence. The blue of Atlas came from the strong emission of the dicarbon molecule C2. Dicarbon, in turn, is created from the breakdown of more complex parent molecules like methane CH4 and acetylene C2H2, trapped in the cometary ice. Therefore, a brilliant blue color equates to an abundant store of these organic compounds. The question is this normal? The answer, not entirely. Comets in our solar system also contain organic compounds. We've known that for a long time. Halley's Comet, studied by the Giotto spacecraft, showed the presence of a lot of carbon. Comet 67P, studied by the Rosetta spacecraft, also detected a whole suite of complex organic molecules, including the amino acid glycine. However, the level of activity and the dominance of the dicarbon emission bands in Atlas were remarkable. It suggests a ratio of organic carbon to water ice that may be higher than in most solar system comets. Think of it like this. Most forests on Earth have oak trees. but there are some special forests where oak trees grow in extreme abundance and dominate the landscape. This tells you that the soil and climate there must be something particularly favorable for oaks. Similarly, the abundance of organic carbon in Atlas suggests the soil and climate of its cradle must have been different, and this is where the red dwarf hypothesis becomes compelling once again, but this time from a chemical perspective. Recall that red dwarf stars emit less high-energy ultraviolet radiation than sun-like stars. UV radiation is the very thing that can break apart complex organic molecules. It acts as a destroyer of chemical bonds. In the chaotic protoplanetary disk where comets are formed, there is a delicate balance. On one hand, radiation from the parent star can drive the creation of complex molecules. On the other hand, it can also destroy them. In a sun-like system with its abundance of UV rays, the destruction process might be more vigorous. This could lead to simpler molecules like carbon monoxide CO and carbon dioxide CO2 being more dominant in the cometary ice. But in a red dwarf system with its gentler radiation environment, the destroyer is weaker. This could create a chemical safe zone where more complex organic molecules like methane and other hydrocarbons can survive, accumulate, and become trapped in the ice at a higher concentration. The red dwarf cradle could act as a more efficient chemical preservative for the precursors of life. Therefore, the chemical fingerprint of Atlas, its brilliant carbon signature, is perfectly consistent with what we would expect from an object born in such an environment. It's not just a comet. It's a comet that carries the chemical flavor of another world. A richer, more organic flavor. The second clue was on the table. The trajectory suggested a common origin, and the chemistry suggested a special low radiation formation environment. Both pointed in the same direction. Our investigation has two crucial clues. The first comes from the orbit. Statistical analysis of the path of 3I Atlas shows it most likely came from the most common type of star in our galaxy. It was not a rare event from a rare source, but likely a common event from a common source. The second clue comes from the chemistry. Its brilliant carbon fingerprint, expressed through its blue color, suggests a special formation environment where complex organic compounds were efficiently preserved, possibly due to lower levels of ultraviolet radiation. Now it is time for the cosmic detectives to place these two clues on the table and see if they point to the same suspect. And the answer is yes, perfectly. Let us officially introduce our prime suspect, the red dwarf star. The orbital clue is explained simply by probability. Our Milky Way galaxy is home to some 200 to 400 billion stars, and of those a staggering 75% are red dwarfs. They are the silent but most numerous citizens of the galaxy. Sun-like stars, the G-type yellow dwarfs, make up only about 7%. The brilliant massive blue stars are even rarer, accounting for less than 1%. So in terms of pure statistics, if you were to close your eyes and point randomly at a star in the galaxy, you would most likely point to a red dwarf. Similarly, if a random interstellar object flies into our solar system, the highest probability is that it was ejected from a red dwarf system simply because there are so many of them. It's like meeting a stranger in a global city. Chances are high they come from one of the most populous nations like China or India. Red dwarfs are the most populous nations of the Milky Way. The orbital clue fits perfectly. Now let's consider the chemical clue. Does a red dwarf fit the description of a special low radiation formation environment? Again, the answer is yes. As we've discussed, red dwarfs are cooler and dimmer than the Sun. They emit most of their energy at longer wavelengths in the red and infrared light. The amount of high-energy ultraviolet UV radiation they emit, especially after their turbulent early life, is significantly lower. This creates a completely different chemical climate in their protoplanetary disks, a gentler environment where complex organic molecules, the precursors to dicarbon, can survive and accumulate in the cometary ice without being too quickly destroyed. So the hypothesis of a red dwarf cradle doesn't just explain why a carbon-rich comet could form, it makes its formation more plausible and likely. The chemical clue also fits perfectly. When two independent clues both point to the same suspect, investigators gain confidence. This is no longer a wild guess. It has become a leading scientific hypothesis, supported by multiple lines of evidence. 3I Atlas was very likely our first messenger from the vastest and most common kingdom in the galaxy, the kingdom of red suns, and so the detective's work is done. The clues have been analyzed. The prime suspect has been identified. The explorer's journey is about to begin. We are ready to leave the world of evidence and step into the world of reconstruction. We will use what we have learned to travel back in time, not just in theory, but with our imagination. We will visit that lost home itself. Our investigation has pointed in a clear direction. The traces left by 3I Atlas from the path it took to the chemical signature it carried all suggest a homeland under the light of a red sun. So what did that world look like? To begin this journey of reconstruction, we must start at the center, at the beating heart of that star system. We must paint a detailed portrait of the parent star itself. It is not a strange star. It is the most common type of star in our universe. But it is entirely different from the Sun we are familiar with. Chapter 2. Portrait of another sun. Let's start with the most intuitive comparison size. Our Sun, a G-type yellow dwarf, has a diameter of about 1.4 million kilometers. It's large enough to fit over 1 million Earths inside. Red dwarfs, in contrast, are tiny. A typical red dwarf, like our nearest neighbor Proxima Centauri, has only about 12% of the Sun's mass. Its diameter is also only about 1/7 that of the Sun. To visualize this with a metaphor, if our Sun were the size of a basketball, a typical red dwarf would be only the size of a tennis ball, or perhaps even a golf ball. They are the true dwarves of the stellar world. This difference in mass is the determining factor for everything else. A star's mass dictates the gravitational force in its core. The stronger the gravity, the higher the pressure and temperature in the core, and the faster the nuclear fusion reactions occur. Because red dwarfs have much less mass, the gravity in their cores is weaker. Therefore, the temperature and pressure are also lower. The nuclear fusion reaction, the process of turning hydrogen into helium, proceeds at a much, much slower rate. This leads to the second major difference: surface temperature. Our sun has a surface temperature of about 500 degrees Celsius, creating a brilliant yellow-white light. A red dwarf with its lower output nuclear reactor has a surface temperature of only about 2,000 to 3,500 degrees Celsius, only about half that of the sun. This lower temperature not only makes them dimmer, but it also determines the color of their light. Every hot object emits a spectrum of light, and the peak of that spectrum, the color it emits most, depends on its temperature. The hotter the object, the more the peak shifts toward blue and violet light. The cooler the object, the more the peak shifts toward red and infrared light. Our sun at 500 degrees has its spectral peak in the green part of the visible spectrum. But because it also emits so many other colors, our eyes perceive the mix as yellow-white. A red dwarf with its much lower temperature has its spectral peak squarely in the red and infrared part of the spectrum. This means that if you were to split the light from a red dwarf through a prism, you would see a very different rainbow. It would be severely lacking in blue and violet colors. Instead, it would be dominated by shades of red-orange and a little bit of yellow. That is why they are called red dwarfs. Their light by its very nature is red, and because they emit most of their energy in the form of infrared, a light our eyes cannot see. Their apparent brightness is even lower. A red dwarf might be only 1/10,000th as bright as the sun. Even our closest stellar neighbor Proxima Centauri is completely invisible to the naked eye despite being just over 4 light-years away. They are the silent, invisible neighbors that make up the majority of our galaxy. We have seen that red dwarfs are tiny, cool, and dim compared to our sun. But this very humility grants them an extraordinary gift, a power that larger stars can never have. That gift is time, an almost infinite amount of time. To understand this, we need to look at how stars live and die. A star's life is a constant battle between two forces: gravity, which is always trying to make it collapse inward, and the pressure from nuclear reactions in the core, which is always trying to push it outward. A star exists as long as it has the fuel to maintain that fight. And for most of their lives, that fuel is hydrogen. Our sun, with its large mass and extremely hot core, burns through its hydrogen fuel at an incredibly fast rate. It's like a gas-guzzling sports car. Every second, the sun converts about 600 million tons of hydrogen into helium. Despite its huge reserves, it will only be able to sustain this process for about 10 billion years. It is currently almost halfway through at 4.6 billion years old. When it runs out of hydrogen in its core, the sun will begin a dramatic end-of-life phase. It will swell into a red giant engulfing the inner planets, including Earth. And finally, it will collapse into a white dwarf, a faint dead stellar core. Its entire story from birth to death lasts about 12 billion years. Now let's look at the red dwarf. Because of their small mass and cooler cores, they burn their fuel extremely slowly and economically. They are like a fuel-efficient car that can go a long distance on a small tank of gas. Their rate of nuclear fusion is thousands, even millions of times slower than the sun's. But that is not the only secret to their longevity. The real secret lies in how they transport energy. In sun-like stars, energy is transported from the core outward, primarily by radiation. This means the helium produced in the core accumulates there like ash in a fireplace, and the hydrogen in the outer layers is never used. The sun can only use about 10% of its total hydrogen, but red dwarfs are completely different. They are fully convective. This means the material inside them is constantly being stirred like a pot of boiling soup. Hydrogen from the outer layers is brought into the core, and helium from the core is brought out. This constant churning allows a red dwarf to use nearly its entire reserve of hydrogen, not just the part in its core. Combining the slow burn rate and the high fuel efficiency, the result is an incredibly long lifespan. The smallest red dwarfs can live for 10 trillion years. Let's pause to reflect on that number. 10 trillion years. Our universe is currently only 13.8 billion years old. This means that not a single red dwarf has ever died in the entire history of the universe. Every red dwarf that was ever born is still in the infancy of its life. They are the witnesses to eternity. When they finally do run out of fuel, trillions of years from now, they will not explode or expand. They will simply slowly shrink, grow dimmer, and turn into a blue dwarf, and then finally a white dwarf, a gentle and silent death. What does this stability mean for the home of 3I Atlas? It means that system, if it still exists, is an incredibly stable place. Its host star will not change its brightness or size for a period of time far longer than the entire history of our solar system. It is a predictable environment, a constant in the universe, and it also means that when 3I Atlas was ejected, its parent star was still very, very young. It had only just begun its long journey, a journey that will witness the birth and death of countless stars like our sun. We have painted a picture of red dwarfs as gentle embers burning steadily for trillions of years. Their long-term stability is an astonishing feature. However, that stability only comes after a long time. When they are young for the first few billion years of their lives, many red dwarfs have a completely different personality. A personality that is violent, erratic, and full of energy. To complete the portrait of the lost home of 3I Atlas, we must also look at the dark side of that piece. We must talk about magnetic fields and their tantrums. Recall that red dwarfs are fully convective stars. The hot plasma inside them is constantly churning like a furiously boiling pot of soup. This chaotic movement of charged plasma creates an extremely powerful dynamo effect. As a result, many red dwarfs have magnetic fields that are hundreds or even thousands of times stronger than the sun's magnetic field. These giant magnetic field lines get twisted and stretched on the star's surface. And sometimes, like a rubber band that's been twisted too far, they suddenly snap and reconnect, releasing a tremendous amount of energy in an instant. This event is called a stellar flare. On our sun, large flares can cause beautiful auroras and sometimes disrupt communication systems. But on a young, active red dwarf, super flares can be thousands of times more powerful. During a super flare, the star can double or even decuple in brightness for a few minutes or hours. It blasts out a huge amount of X-rays and high-energy particles into space. For any planet orbiting nearby in the habitable zone, these firestorms would be catastrophic. They could easily erode and completely strip away a planet's atmosphere and irradiate the surface with a lethal dose of radiation. So life under a crimson sky might not be peaceful at all. It could be a precarious existence constantly threatened by the sudden tantrums of the parent star. The home of 3I Atlas was most likely formed in such a volatile environment. It was forged in fire. Another characteristic of red dwarfs is how they change over time. As a red dwarf gets older, its rotation slows down. Its magnetic activity also decreases. The flares become less frequent and weaker. After a few billion years, they truly do become gentle, stable embers. This has an important implication for the possibility of life. Perhaps life cannot arise during the violent early phase of a red dwarf, but it might have a chance in the trillions of years of stability that follow. When 3I Atlas was formed and ejected, its parent star was likely still in its young active phase. It would have witnessed these firestorms from a distance from the safety of its cometary belt. The portrait of its home is now more complete. A tiny, long-lived sun, but also with a violent youth, a powerful magnetic field, and sudden tantrums. A world of contrasts, a balance between persistence and volatility. And it was in this complex world that planets and comets were born. We have painted a detailed portrait of the parent star, a red, long-lived, and volatile sun. Now it is time to expand our view outward to explore the worlds that might be orbiting it. What kind of planets could exist in such a system? And more importantly, could there be a place in that system where life as we know it could exist? To answer that question, astronomers begin by searching for a very special region, a precious and narrow band of orbits where the conditions are just right. That region is called the habitable zone. Chapter 3: Worlds Under Twilight. The habitable zone, also known as the Goldilocks zone, is a simple but powerful concept. It defines the orbital region around a star where the temperature on the surface of a planet with a suitable atmosphere could allow liquid water to exist. Not too hot where the water would boil away, not too cold where the water would be permanently frozen, but just right. For life as we know it, liquid water is an essential solvent, a cradle for complex chemical reactions. Therefore, the search for extraterrestrial life often begins with the search for planets within their host star's habitable zone. In our solar system, the habitable zone is quite wide. It starts somewhere near the orbit of Venus and extends out past the orbit of Mars. Our Earth, of course, sits perfectly in the middle of this zone, but the location and size of the habitable zone are not fixed. It depends entirely on the parent star. Imagine you are sitting around a campfire. If it's a big roaring fire, you have to sit far away to feel comfortably warm. If you sit too close, you'll get burned. If it's just a small flickering fire, you have to huddle in close to feel the warmth. If you sit too far away, you'll be cold. This principle is exactly true for stars. Our sun is a big roaring fire. Its habitable zone is located at a safe distance, starting from about 150 million kilometers. Red dwarfs, as we know, are much smaller and cooler fires. They emit significantly less energy. Therefore, to receive the same amount of energy to get the just right temperature for liquid water, a planet would have to orbit much, much closer to its red dwarf star. The habitable zone of a typical red dwarf might be 20 times closer than the Sun's. It could be located well inside the orbit of Mercury in our solar system. This creates a very different planetary system architecture. The potentially habitable planets would be huddled very close to their parent star. A year on such a planet might last only 10, 20, or 30 Earth days, and this proximity leads to a series of strange and complex consequences that would completely shape the nature of these worlds. It brings both opportunities and immense challenges for potential life. We have identified the potential oasis for life in a red dwarf system, a narrow orbital zone close to the parent star. But this proximity comes at a price that completely shapes the nature of any world that exists there. When a planet orbits very close to its star, the star's immense gravity pulls on the planet unevenly. The nearer side of the planet is pulled slightly more strongly than the farther side. This differential force, called a tidal force, acts like an invisible brake, slowly decelerating the planet's rotation over millions of years. Eventually, the planet's rotation period will synchronize with its orbital period. The result is a strange stable state known as tidal locking. Tidal locking means one side of the planet will always face the star, and the other side will always be cloaked in darkness. We are familiar with this phenomenon. Our moon is tidally locked to the Earth, which is why we always see only one face of it. But for a planet in the habitable zone of a red dwarf, the consequences of this are enormous. It creates a world of two eternal extremes. Let's explore that world. The day side. This is a world of unending day. The red dwarf star would hang motionless in the sky, perhaps directly overhead, never rising, never setting. This surface would be perpetually irradiated by the star's light and energy. If the planet lacks a thick enough atmosphere or oceans to distribute the heat, the day side could become a scorching desert where liquid water would be boiled away into the atmosphere. It would be a world baked under a never-setting twilight. The night side. On the opposite side of the planet lies a world of eternal darkness and cold. There is never any direct sunlight. The sky would be a black canvas dotted with distant stars. This surface would constantly lose heat to space. Without a strong enough atmosphere to trap warmth, it could become a frozen wasteland where any gases, including carbon dioxide, might freeze solid onto the surface. It would be an unending ice age, a world of fire and ice separated by the planet itself. Clearly, neither of these extremes is ideal for life as we know it, but there is a third place, a place in between. The Terminator Zone. This is the narrow strip of land that lies between the day side and the night side, a region of eternal twilight and dawn. On this strip of land, the red dwarf star would always be on the horizon, never rising higher, never setting lower. The light would be slanted like during early morning or late afternoon on Earth, and it is here that the temperature could be just right. It would be warm enough for water to exist as a liquid, but not so hot that it boils. It would be cool enough not to be scorched, but not so cold as to be frozen. Many scientists believe that if life exists on a tidally locked planet, the Terminator Zone is the most likely place. It is a temperate oasis running in a circle around the planet. However, life here would also be very unusual. Extremely strong winds would likely blow constantly from the hot day side to the cold night side, creating a violent global weather system. Any photosynthetic organisms would have to adapt to a light source that always comes from a single direction. Trees might grow tilted toward the horizon. One side of every mountain, every valley would always be in light, and the other side would always be in shadow. It is a world of permanent contrast, a world without the day-night rhythm we are so accustomed to. And it is in these strange gravitationally locked worlds that the lost home of 3i Atlas might have existed. We've discovered a potential oasis, the Terminator Zone, of a tidally locked planet where the temperature might allow liquid water. But what would such a world look like if life were to arise? This is where we enter the realm of speculative astrobiology. We have no firm answers, but based on what we know of physics and biology, we can paint some fascinating pictures of an alien ecosystem. Let us together imagine life under a red sun. The first thing to consider is the light. The light from a red dwarf, as we know, is mostly in the red and infrared part of the spectrum. It lacks the blue and violet light that plants on Earth use so effectively. Chlorophyll, the pigment that makes our plants green, is optimized to absorb blue and red light. It reflects green light, which is why we see them as that color. On a planet orbiting a red dwarf, green chlorophyll would be a very inefficient choice. Instead, astrobiologists speculate that plants there would likely evolve different photosynthetic pigments, ones designed to absorb as much red and infrared light as possible. To absorb all wavelengths of light, what color would the most efficient pigment be? It would be black. So it's possible that the forests on such a world would not be green. They might be forests of black with dark leaves to capture every precious photon from the twilight sun. Or they could be a deep purple or even colors we cannot imagine if they use entirely different chemical mechanisms. A landscape of black forests under a dark orange sky. A truly alien image. And what color would the sky be? Red light has a longer wavelength and is not scattered by atmospheric molecules as much as blue light. Therefore, the daytime sky might not be brightly colored. It could be a pale yellow-orange or even beige. The red dwarf star would appear as a large, deep red orb hanging against that backdrop. Animals, if they existed, would also have to adapt. Creatures living in the Terminator Zone might have larger eyes to gather more of the dim light. Some might even evolve the ability to see in the infrared, to be able to see the temperature of their surroundings. But the biggest challenge for life would not just be the light. It would also be the violent flares from the parent star. Some scientists argue that these flares would make surface life impossible, but life is resilient. Perhaps life would not develop on land but underwater. A sufficiently deep ocean could act as an effective shield protecting the organisms living below from the lethal doses of radiation from the flares. So perhaps the true oasis for life would not be the terminator zone on land, but the global oceans warmed by a red sun. Whatever the scenario, one thing is clear: life, if it exists in a red dwarf system, would be very different from us. It would be shaped by entirely different conditions. A sun that never sets a light of a different color, and a constant threat from the stars' tantrums. And it was in such a hypothetical, strange, and challenging world that the lost home of Three-Eye Atlas might have existed. But our traveler did not come from a habitable planet. It came from a place even farther and colder. It is time for us to leave the warm oases and journey out to the icy periphery of this star system. We have journeyed through the hypothetical worlds that might exist close to the red dwarf star, tidally locked planets with eternal twilight skies. But the true home of our traveler, the cradle that created it, was not in those warm regions. Like all comets, it is a creature of the cold. It was born in the outer reaches of its star system, a place far enough for ice to survive and condense. To find this icy nursery, we must identify one of the most important and invisible boundaries in any planetary system. That boundary is called the frost line. Chapter 4. The Icy Nursery. The frost line, also known as the snow line, is a very intuitive concept. It is the distance from a star at which the temperature is cold enough, typically around minus 120 degrees Celsius, for volatile compounds like water, ammonia, and methane to condense into solid ice particles. Imagine you are moving away from a campfire. Close in, it's too hot for snow to exist. But as you move far enough away, you reach a point where snow can begin to accumulate on the ground. That point is the frost line. In a protoplanetary disk, the frost line is a critically important boundary. It divides the star system into two distinct chemical zones inside the frost line. Near the star, only high-temperature materials like rock and metal can exist in solid form. This is the rocky zone, where terrestrial planets like Earth, Mars, Venus, and Mercury are formed, outside the frost line. In this cold region, there is not only rock and metal, but also a huge amount of ice. Water ice is the most common, but there are also ices of other gases. The amount of solid material here is much greater than in the inner zone, allowing for the formation of gas giant planets like Jupiter and Saturn, and of course, billions of comets. The location of the frost line depends entirely on the brightness of the parent star. The hotter and brighter the star, the farther out it pushes the frost line. In our solar system, with a relatively bright sun, the frost line is located somewhere between the orbits of Mars and Jupiter, about 400 to 450 million kilometers from the Sun. This is why the inner planets are all rocky, and the giant planets are all on the outside. Now let's return to our red dwarf system. As we know, red dwarfs are much cooler and dimmer than the Sun. They emit significantly less energy. Therefore, to reach the same condensation temperature, the frost line in a red dwarf system will be located much, much closer to its parent star. It wouldn't be out beyond the orbit of Mars, but could be well inside the orbit of Earth, or even closer. This means the entire architecture of the planetary system would be compressed. The rocky zone would be smaller, and the icy kingdom would begin at a much closer distance. The nursery where 3I Atlas was born, the land of icy planetesimals, might have been located at a distance that in our solar system we would consider the inner region. This has interesting consequences. Although colder, this comet-forming region might receive more radiation from the young star's flares than comets in our solar system. The chemical environment here, though cold, was not entirely static, and it was at this fragile boundary between the world of rock and the world of ice in a region of space much closer than we might think that the chaotic memory of the formation of 3I Atlas took place. We have identified the location of the nursery, a cold region of space lying beyond the frost line, but much closer to the red dwarf star than we might imagine. But location is only part of the story. To truly understand why 3I Atlas became a carbon comet, we must look at the raw materials available in that nursery. We must analyze the chemical composition of the protoplanetary disk and how it was affected by the unique light of a red sun. This is where we find the most important clue to explain its later blue color. The protoplanetary disk around a young star isn't just dust and ice. It is an extremely complex chemical soup. It contains the basic elements created in the Big Bang like hydrogen and helium. It also contains the heavier elements forged in previous generations of stars and seeded into space like carbon, oxygen, nitrogen, and silicon. Under the influence of the physical conditions and the radiation from the central star, these elements combine to form a whole host of molecules. In the cold region beyond the frost line, we have simple molecules like water, H2O, carbon monoxide, CO, carbon dioxide, CO2, methane, CH4, and ammonia, NH3. But that's not all. The radiation from the star can also drive the formation of more complex organic molecules. Hydrocarbon chains, aromatic ring compounds, and even the precursors to amino acids. All of these molecules, both simple and complex, are frozen and mixed with rocky dust grains, forming the basic bricks to build comets. And this is where the difference between a sun-like system and a red dwarf system becomes critically important. Recall that radiation from a star is a double-edged sword. It can both create complex molecules and destroy them. High-energy ultraviolet UV light acts as a double-edged sword. It can provide the energy for chemical reactions, but if it's too intense, it will break complex molecules down into smaller, simpler fragments. It is a destroyer of chemical bonds. In the early solar system with a young and active sun, the amount of UV radiation was abundant. The environment in the protoplanetary disk may have been quite harsh chemically. The destruction process could have been vigorous. This might have led to simpler, more robust molecules, like carbon monoxide, CO, and carbon dioxide, CO2, being more dominant in the chemical makeup of comets. More complex organic molecules, while still present, might not have been able to accumulate to very high concentrations. Now let's turn to the red dwarf system. As we know, the parent star here is cooler and emits significantly less high-energy UV radiation. The chemical environment in its protoplanetary disk is therefore gentler. The UV scissors are weaker. The process of destroying complex molecules happens at a slower rate. This creates a chemical safe zone, a more favorable environment where more complex organic molecules like methane, CH4, acetylene, C2H2, and longer hydrocarbon chains can survive, accumulate, and become trapped in the ice at a much higher concentration. The red dwarf cradle isn't just a freezer. It is a more effective chemical preservative. It favors the preservation of the organic heritage of the original molecular cloud. Therefore, the comets formed in this icy nursery are by their nature likely to be much more organically rich than comets in our solar system. They are supercharged with the precursor molecules of carbon, and this is the key to explaining the blue color of 3I Atlas later on. It was not a random event. It was the direct result of the chemical legacy it carried from its lost home, a home illuminated by a gentle light, a home that allowed the building blocks of life to accumulate in silence and darkness. But we have the raw materials. A rich chemical soup full of organic compounds floating in the icy outer reaches of the red dwarf system. But how do you turn this thin soup into a solid object, a kilometer-wide comet? Now we shift from the story of chemistry to the story of physics, the story of accretion of gravity, and of the patience of the universe. This is the process of the traveler's own formation, a process that may have unfolded at a slightly different rhythm than in our solar system. The formation of comets or planetesimals begins with very small things. Tiny dust grains and ice crystals of micrometer size begin to collide and stick together due to static electricity, like dust bunnies clinging to your clothes. They form larger clumps of millimeter then centimeter size. As they get larger, static electricity becomes weaker and a barrier emerges. High-speed collisions can shatter them instead of making them grow. This is where other mechanisms come into play. One of the leading ideas is the streaming instability. Imagine these icy pebbles orbiting the star within a disk of gas. They don't move at the same speed. The gas tends to move slightly slower due to pressure. This speed difference creates a headwind for the pebbles, causing them to slow down and drift inward toward the star. However, this drift is not uniform. In some regions, the pebbles can accidentally clump together, creating a denser region. This region will then create more drag on the gas, slowing the gas down. This in turn reduces the headwind inside the clump, allowing more pebbles to be drawn in. A positive feedback loop is created. The clumps of pebbles become denser and denser until they reach a critical point. At that point, the clump's own self-gravity, previously negligible, becomes strong enough for it to collapse. It collapses rapidly in a few thousand years to directly form a solid body tens or hundreds of kilometers wide. This is not a slow brick-by-brick accretion process. It's more like a cosmic avalanche forming a giant snowball in an instant. 3I Atlas was very likely born from such a collapse event. So how might this process be different in a red dwarf system? There are two main factors. First, because the red dwarf system is smaller and has less mass, its protoplanetary disk may also have less mass and be less dense. This means the accretion process might be slower. There is less material and collisions happen less frequently. The time it takes to form a comet the size of Atlas might be longer than in the solar system, but red dwarfs have plenty of time, so this is not a problem. Second, the closer location of the frost line may play a role. Although still cold, this comet-forming region is closer to the star, meaning it's more strongly influenced by the star's gravity. The density of the gas disk might also be higher. These conditions could affect the efficiency of the streaming instability mechanism. Some models suggest it could work more efficiently, while others suggest the opposite. This is still a very active area of research, but the end result was an icy body, a planetesimal, had been formed. It was a loose collection of ice and dust, not a solid rock. It was likely very porous with a lot of empty space inside. It preserved intact the chemical composition of the region of the disk from which it had collapsed. The rich organic heritage was locked deep within it, and now it was a complete entity, beginning its life as a member of the cometary belt, silently orbiting its red sun, waiting for an event that would change its destiny forever. Our traveler has been born. An icy planetesimal rich in organic compounds is silently orbiting in the cometary belt of a red dwarf system. In an ideal scenario, it could have stayed there for billions of years, a peaceful and predictable existence. But early planetary systems are rarely peaceful. They are volatile places, stages for complex and sometimes catastrophic gravitational dances. To understand why 3I Atlas was ejected from its home, we must introduce the main characters of this play, the gas giant planets. And we must understand that these giants rarely stay in one place. Chapter 5, The Chaotic Dance. In the early models of solar system formation, scientists assumed that planets were born and raised in the orbits we see them in today. Jupiter was always where Jupiter is. Saturn was always where Saturn is. But as we began to discover planetary systems beyond our own exoplanets, we saw strange things. We found giant gas planets, hot Jupiters, orbiting closer to their parent stars than Mercury. According to theory, a gas giant planet cannot form in such a hot place. It needs to be formed outside the frost line, where there is enough ice to quickly build a massive core and gather gas. This discovery led to a revolution in our understanding. Scientists realized that planets, especially the largest ones, do not stay put. They can move or migrate through their star systems during their early lives. The main mechanism behind this migration is the interaction with the protoplanetary disk, the very disk of gas and dust that created them. Imagine a newly formed gas giant planet. It is still embedded in the gas disk. As the planet orbits the star, its gravity creates density waves in the disk, much like a boat creates a wake as it moves through water. These waves, both in front of and behind the planet, then exert a gravitational pull back on the planet itself. This complex interaction can create a torque. Depending on the conditions in the disk, this torque can cause the planet to lose orbital energy and slowly spiral inward toward the star. This process is called Type 2 migration, or in some cases, it can cause the planet to gain energy and slowly spiral outward. The migration of giant planets is one of the most powerful shaping processes in an early star system. A giant migrating inward can clear out any smaller terrestrial planets in its path. A giant migrating outward can stir up the asteroid and comet belts causing a period of chaos. They are the architects, but also the wrecking balls of planetary systems. In our own solar system, we have strong evidence that migration occurred. A leading model called the NICE model proposes that Jupiter, Saturn, Uranus, and Neptune were originally formed in much closer orbits to each other. Then, due to gravitational interactions, they went through a period of instability, which caused Uranus and Neptune to be flung out to their current, more distant orbits, while Jupiter moved slightly inward. This very migration is thought to have caused the late heavy bombardment, a period in the early history of the solar system when asteroids and comets from the outer belts were thrown inward, creating the countless impact craters we still see on the moon today. So there is no reason to believe that the red dwarf system, the home of 3I Atlas, did not experience a similar process. It is very likely that in that system, one or more gas giant planets also formed, and it is very likely that those giants also did not stay put. They migrated, and the dance of these wandering giants is what stirred up the icy nursery and created the chaos needed to change our traveler's destiny. We have introduced the main characters of this chaotic play migrating gas giant planets, but the migration of a single planet is often a relatively slow and controlled process. To create a large-scale instability, an event that can stir up an entire comet belt, you often need a trigger. A special event that makes the dance of the planets dangerous. That trigger in many cases is a phenomenon that is mathematically beautiful, but can be physically devastating. That phenomenon is called an orbital resonance. An orbital resonance occurs when two objects orbiting a third central body have orbital periods that are related by a ratio of simple integers. It sounds complex, but the idea is very intuitive. Imagine two runners on a circular track. If one runs exactly twice as fast as the other, then for every 2 laps the faster runner completes, the slower runner will complete exactly 1. They will meet at the same point on the track at regular intervals. This is a 2-1 resonance. In the solar system, we see many examples of this. Jupiter's 3 largest moons, Io, Europa, and Ganymede, are locked in a 4-2-1 resonance. For every 4 orbits, Io completes Europa completes exactly 2, and Ganymede completes exactly 1. Pluto and Neptune are also in a 3-2 resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. When planets fall into a resonance, they begin to talk to each other much more effectively. Normally, the gravitational pull of one planet on another gets averaged out over time, as they are in different positions in their orbits. But in a resonance, they meet at the same point in their orbits repeatedly. This allows the small gravitational nudges to add up over time, like pushing a swing in rhythm. Each small push makes the swing go higher and higher. This accumulation of gravitational force can dramatically change the shape and inclination of the planet's orbits, pulling them out of their stable near-circular paths. Now let's go back to the NICE model of our solar system. Scientists believe the Great Instability Phase was triggered precisely when Jupiter and Saturn, during their migration, passed through and became locked in a 2-1 orbital resonance. This moment of resonance acted like a ringing bell. It sent energy and instability throughout the entire outer planetary system. It amplified the small gravitational interactions, turning them into giant pushes. It woke up the sleeping giants and started a chaotic dance. There is no reason to believe that red dwarf systems would be immune to this phenomenon. In fact, because the planets in red dwarf systems orbit closer together, the gravitational interactions between them are even stronger. The likelihood of them falling into resonances during migration is even higher. Imagine the scenario in the lost home of 3I Atlas. Perhaps two giant planets had formed and were slowly migrating. Their orbits were getting closer and closer, and then they reached a critical point, a golden ratio of destruction, maybe 3:2 or 2:1. Instantly, the system, which had been relatively stable, was thrown into chaos. The planets began to pull and push each other violently. Their orbits became eccentric, elongated. They might have swapped places. One planet might have even been thrown out of the system entirely. The symphony of gravity had turned into a blaring rock concert, and this chaos at the center created a gravitational tsunami that spread out to the periphery. It reached the icy nursery. The orbital resonance between the gas giants had sounded the bell for the end of a peaceful era. The instability from the center spread outward like a gravitational tsunami, and it crashed into the icy nursery where billions of comets, including 3I Atlas, were orbiting in stable, near-circular paths. What happened next was one of the most violent and formative periods in the history of a planetary system, a period that scientists call the heavy bombardment, a cosmic game of billiards on an unimaginable scale. Before the instability, the comet belt was like a vast, orderly river. All objects moved in the same direction on nearly parallel paths. Collisions were relatively rare, but when the gravitational tsunami from the giant planet's resonance hit the entire belt, was violently stirred up. Imagine taking a large stick and stirring a river vigorously. The orderly flow disappears, replaced by whirlpools, countercurrents, and chaos. The changing gravity of the migrating giant planets did the same thing to the comets. Their orbits, previously near-circular, were stretched into eccentric ellipses. Their inclinations relative to the plane of the system were also altered. The entire comet belt, once a river, had become an agitated swarm of bees. Billions of icy bodies, each kilometers wide, were now flying on chaotic, crisscrossing orbits at enormous speeds. The number of collisions increased exponentially. These were no longer the gentle kisses that helped them grow. These were high-energy, head-on collisions. They shattered comets into smaller pieces, creating trillions of new fragments and a huge amount of dust. The icy nursery had turned into a shooting gallery, and most importantly, the stirring began to throw comets out of their safe belt. Some were thrown into the inner system toward the rocky planets and the parent star. They became cosmic bullets, causing giant impacts that may have delivered water and organic compounds to the inner planets, but could also cause destruction. Others were thrown outward. In the chaotic dance of gravity, a comet like 3I Atlas, as it passed near a moving gas giant, could receive one final gravitational push. This was the moment of destiny. This chaotic dance was not just a random event. It was a clearing mechanism. A mechanism that reshaped the entire architecture of the star system. It cleared out most of the leftover material either by throwing it into the star or by ejecting it into interstellar space. For 3I Atlas, this was the climax of its chaotic memory. It had survived millions of years of collisions to be formed. It had experienced a long period of peace, and then it was caught in a cosmic storm, a storm created by the dance of its giant siblings. This storm tore it away from its family. It set it on a new path, a path leading outward into the unknown. The chaotic dance was over. The life in exile was about to begin. The storm of comets had stirred up the entire periphery of the star system. Stable orbits were a thing of the past. Billions of icy bodies, including 3I Atlas, were now flying on chaotic, crisscrossing paths. Most of them would end up colliding with each other, or being thrown into the parent star, or eventually settling into new orbits. But for a small few, this storm was just the beginning of a much grander journey. This is where we delve into the decisive moment, the moment that transformed 3I Atlas from a member of a star system into a traveler of the Milky Way. This is the story of the final push. Chapter 6. The moment of ejection. In the chaotic dance of gravity, the eccentric orbit of 3I Atlas brought it onto a collision course with one of the system's gas giants, a migrating behemoth. As it drew near, one of the most powerful and subtle phenomena in the universe occurred. A phenomenon we call a gravitational assist, or more intuitively, a gravitational slingshot. This is not a mysterious force. It is a perfect exchange of energy governed by the laws of Newton. Imagine the concept simply. You are skateboarding on a straight path at 10 kilometers per hour. Ahead of you, a large bus is moving in the same direction at 50 kilometers per hour. If you could grab onto the back of the bus for a moment, you would be pulled along your speed, rocketing up to match the buses. And when you let go, you would continue hurtling forward at 50 kilometers per hour. You have been accelerated by 40 kilometers per hour. Now, imagine a more complex scenario. You are standing still. The bus hurtles toward you. Just as it gets close, you throw a tennis ball at the front of the bus. The ball hits the bus and bounces back. At what speed will it bounce back? Not just its original speed. It will bounce back with its original speed plus the speed of the bus. It has stolen a piece of energy from the bus's motion. The gravitational slingshot works on a similar principle. The gas giant is the moving bus, and 3I Atlas is the tennis ball. As 3I Atlas approached the giant planet, it fell into the planet's deep gravity well. It was pulled closer, and its speed increased dramatically as it fell toward the planet. It did not collide. It looped around the back of the planet in a hyperbolic trajectory. In the brief moment it was closest, it was latched on to that powerful gravitational field and was dragged along with the planet for a short distance in its orbit around the star. In that moment, an exchange of energy took place. 3I Atlas stole a tiny fraction of the giant planet's orbital energy. For a planet with a mass hundreds or thousands of times that of Earth, this energy loss is immeasurable. Its orbit might change by a few centimeters, but for a tiny object like a comet, the amount of energy transferred was enormous. After looping around, it was flung out of the gravity well like a stone from a moving slingshot. It left with a much higher velocity than when it arrived, and this new speed surpassed one final critical threshold, the most important threshold of all, the escape velocity of the entire star system. Escape velocity is the minimum speed needed to completely overcome the gravitational pull of a central body and never return. The escape velocity from Earth is about 11 kilometers per second. The escape velocity from the solar system at our distance is about 42 kilometers per second. Before the encounter, 3I Atlas did not have that speed. But after the push from the gravitational slingshot, it had more than enough. The final gravitational tether, the cord connecting it to its parent star, had been broken. We have used this very technique to explore our own solar system. The Voyager 1 and 2 spacecraft launched in the 1970s did not have enough fuel to fly to the outer planets. Instead, they performed a grand tour, using a gravitational slingshot from Jupiter to accelerate toward Saturn. Then they used Saturn to accelerate toward Uranus, and so on. Each gravitational assist was a free refueling from the universe. It was these pushes that allowed the Voyager probes to achieve escape velocity from the solar system and begin their own interstellar journeys. 3I Atlas experienced a similar process not by design, but by cosmic chance. The final push had been made. The one-way street was open. The laws of physics were set. The energy had been exchanged. The fate was sealed. But let's for a moment step away from the equations and graphs. Let's try to imagine the moment itself, not from the perspective of an observing scientist, but from the perspective of the traveler itself. Of course, a comet has no eyes, no feelings. But if we could assign it an experience, a memory of the most momentous event in its life, what would it look like? This is an act of scientific imagination, an attempt to feel the grandeur of a departure. For millions of years, its world had been a predictable repetition, a long, slow orbit around a red sun. But after the storm of the heavy bombardment, everything had changed. Its orbit was now eccentric, taking it into regions of space it had never been. And then it began to feel a new pull, not the familiar pull from the parent star at the center, but a pull from the side, a pull that grew stronger and stronger. Ahead of it, a giant was growing larger. A gas planet, perhaps larger than Jupiter, with colorful cloud bands and a faint ring system. For it, this was the first time it had come so close to another world. It began to fall. Its speed increased dramatically, from a few kilometers per second to tens of kilometers per second. It was hurtling toward the giant. Its path was violently bent. It was no longer following a gentle curve around its parent star. It was making a sharp turn, pulled into an intimate and dangerous dance. As it skimmed the highest cloud tops of the gas planet, its world was plunged into darkness for a moment as it passed behind the planet. Then it emerged again, bathed in the twilight reflected from the clouds. It might have passed near one of the planet's icy moons, seeing the craters and fissures on their surfaces. The entire event may have lasted only a few days or weeks, but in that short time it was extraordinarily accelerated. And then it was thrown out. As it escaped the planet's gravity well, it felt a new freedom. It was no longer being pulled back. It was flying outward, faster than ever before. And this is when the most important visual memory was formed. As it looked back, it saw two things. It saw the giant gas planet, the one that had given it its final push, shrinking behind it, and further beyond it, saw its parent star, the glowing ember that had been the center of its existence for millions of years. But now that star was no longer ahead, no longer the point to which it would return. It was behind, and it was getting smaller. Day by day, week by week, its parent star grew fainter, from a brilliant orb to a bright star to a point of light. And finally, after thousands of years, it blended in with the countless other points of light in the sky. Its home had become a stranger star. There was no force pulling it back. There was no dance to rejoin. Ahead of it, there was only darkness and the unknown. The memory of home was closed. The forgotten memory. The long journey through the ocean of silence had officially begun. The memory of the ejection of 3I Atlas is a dramatic and emotional story. A single individual was severed from its home and began an aimless journey. But to truly understand its place in the universe, we must recognize an important truth. Its story is not unique. It is just one story among trillions of similar stories that have been and are still unfolding across the Milky Way. It is time for us to look at the true scale of this event. The process of dynamical instability, the migration of gas giants, and the gravitational slingshot effect are not rare events. Scientists believe this is an almost mandatory phase in the evolution of most planetary systems, including our own. In their chaotic early lives, every star system acts as an efficient launcher of comets and asteroids. Computer simulations estimate that for every one comet remaining in our own Oort cloud, there could be tens or even hundreds of other comets that were completely ejected from the solar system. Now let's scale that up. Our Milky Way galaxy has some 200 to 400 billion stars. If we assume that a large fraction of those also form planetary systems and comet belts, and also experience a similar phase of instability, then the number of interstellar objects wandering the galaxy is an unimaginable number. Trillions, quadrillions. The space between the stars is not empty. It is a sea of exiles. 3I Atlas was not a lonely traveler in the sense that it was the only one. It was only lonely in the vastness of the distance. In fact, it is a member of a huge population, an invisible nation of homeless objects. At any given moment, scientists estimate there could be thousands of interstellar objects the size of Oumuamua or Atlas passing within the orbit of Earth. We just don't see them because they are too small, too faint, and move too fast. Oumuamua, Borisov, and Atlas were not miraculous rare events. They were just the first ones we had the technology to detect. They are the first drops of a coming rain. This completely changes our perspective. The universe is not a collection of isolated island star systems. It is an interconnected ecosystem constantly exchanging material. Fragments from our system are traveling to other stars, and fragments from other stars are traveling here. 3I Atlas was not just a visitor, it was proof of that connection. And it is in this sea of exiles that one of the most fascinating ideas in science finds a potential mechanism. We have followed our traveler on a grand journey. From its birth in a crimson cradle, to the moment of its ejection by a chaotic dance of planets, and finally to its entry into the sea of exiles. The entire story of its lost home is a reconstruction based on physical and statistical clues. But now it is time for us to return to the most solid evidence, the evidence we could observe directly. The evidence that started this investigation in the first place. Its chemical legacy, the signature written in blue. Chapter 7. The chemical legacy. Let's summarize the chemical profile of 3I Atlas. The most important piece of evidence, as we have explored in detail, was its brilliant blue color. Spectroscopy told us with certainty that this color came from the strong emission of the dicarbon molecule C2. This was not a singular observation. It was an undeniable fingerprint, a cosmic barcode that screamed one word: carbon. The emission of dicarbon is in turn a secondary product. It is created from the breakdown of more complex parent molecules, organic compounds trapped in the ice when they are released and exposed to sunlight. Therefore, the logic is clear. A brilliant blue color created by dicarbon equates to an unusual abundance of organic compounds in the comet's original composition. 3I Atlas was not just a comet, it was an organic comet, and this is where the entire story of its lost home connects perfectly. Why is this abundance of organic carbon such an important clue? Because it is not entirely typical of what we see in most comets in our solar system, and it is perfectly consistent with what we would expect from an object born in the special environment of a red dwarf system. Let's connect the dots. In Chapter 4, we discovered that the protoplanetary disk around a red dwarf has a gentler chemical climate because the parent star is cooler and emits less high-energy ultraviolet radiation. The UV scissors that break apart complex molecules are weaker. This creates a more favorable environment where more complex organic molecules like methane, acetylene, and other hydrocarbon chains can survive, accumulate, and become trapped in the ice at a higher concentration. The red dwarf cradle acts as a more effective chemical preservative for the precursors of life. Therefore, the chemical legacy that 3I Atlas carried, its brilliant carbon signature, was not a coincidence. It is a fossil record, a direct proof of the conditions in the icy nursery where it was born billions of years ago. It's like a geologist analyzing the composition of a rock and being able to say, this amount of this mineral shows this rock was formed under extreme pressure and temperature deep within the Earth. Similarly, astronomers look at the spectrum of Atlas and can say, this amount of organic carbon suggests this comet was most likely formed in an environment with low UV radiation, such as around a red dwarf star. The entire story has come full circle. The trajectory pointed to a type of home. The chemistry confirmed that the climate of that home was a perfect match for what was observed. The chemical legacy of Atlas is not just an interesting feature, it is the final confirmation seal for its origin story. It is the indelible signature of its lost home. We have connected the chemical legacy of 3I Atlas to its lost home. A gentle red dwarf cradle allowed it to accumulate a treasure trove of organic compounds. But that only explains why it was supercharged with fuel. It doesn't explain why its engine ran so powerfully, why the blue performance was so brilliant and spectacular. The answer lies in a perfect combination and interaction between the past and the present. It is the story of a seed nurtured in one environment, and then planted in a completely different one. Let's consider the two key factors in the chemical factory of the coma that produced the dicarbon. The first factor is the amount of raw material. That is the amount of organic parent molecules like methane and acetylene available in the ice. The second factor is the efficiency of the machine. That is the amount of ultraviolet UV radiation from the sun, which acts as the invisible scissors to break apart those parent molecules. To create a spectacular show, you need both a lot of fuel and a very powerful machine, and 3i Atlas had both thanks to its unique journey. Think of it like this. Phase 1. Accumulation. During its millions of years of formation and existence in the red dwarf system, it was supercharged with fuel. The low UV environment allowed a large amount of organic compounds to be preserved and accumulated in its nucleus. It was like a warehouse filled with barrels of chemical gunpowder. Phase 2. Transit. The billion-year journey through interstellar space perfectly preserved that cargo in the deep cold. The dark crust created by cosmic rays acted as an additional protective layer. And then, Phase 3 activation. The traveler carrying its precious cargo flew into a completely new environment, our solar system. And our sun, a yellow dwarf, is an extremely powerful machine. It emits an abundant and powerful stream of UV radiation, much more so than the parent star of Atlas. What happened next was a perfect chemical storm. A comet supercharged with organic compounds from a red dwarf system, flying into a sun-like system with its abundance of UV rays, created a hyper-efficient dicarbon production factory. The huge amount of raw material met an extremely powerful machine. The intense sublimation released a massive amount of parent molecules into the coma, and the strong UV flux from the sun broke them down quickly and efficiently, creating a rain of free radicals and subsequently an ocean of dicarbon molecules. The result was an explosion of blue light. It wasn't just fluorescence, it was a superfluorescence. The uniqueness of Atlas came not just from where it was born, it came from the combination of where it was born and where it arrived. It's like taking a rare oily wood from a tropical forest, the red dwarf system, and throwing it into a roaring furnace, the solar system. The flame would erupt with a unique intensity and color very different from just throwing in a regular piece of pine. 3 Atlas was that rare piece of wood. Its spectacular performance was a direct consequence of its interstellar journey. It is a reminder that the most beautiful phenomena sometimes happen at the intersections, at the meeting points between two different worlds. And that blue color is the final evidence, the smoking gun that reinforces the entire story of its lost home. We have put all the pieces of the puzzle together. A journey that began with scattered clues has led us to a complete and logical story. A story of a home under a twilight sun. A story of exile and a long journey through the darkness. And a story of awakening in a new world. Every step on this path has been supported by evidence and scientific models, but every investigation needs a concluding moment, a final, irrefutable piece of evidence that ties everything together. For the story of the lost home of 3i Atlas, that final piece of evidence is the blue. Let's review the entire case. Evidence A. the orbit. Statistical analysis shows our traveler most likely came from a red dwarf system, the most common type of star in the galaxy. Evidence B. The chemistry. Its spectrum reveals an unusual abundance of organic carbon compounds, a feature consistent with the low UV formation environment of a red dwarf system. Evidence C. The performance. Its brightness outburst and brilliant blue color are perfectly explained by the combination of an organically supercharged comet from a red dwarf system entering the UV-rich environment of our solar system. All the evidence points in the same direction. It is not just compatible, it is mutually reinforcing. The blue color is not just a consequence, it is a prediction. If our hypothesis is correct that comets from red dwarf systems are more organically rich, then we would expect that when they fly into our solar system, they would produce a spectacular dicarbon show. And that is exactly what we saw. 3I Atlas behaved exactly as a messenger from a red dwarf system should. It's like in a courtroom. The prosecutors have presented the motive and the opportunity. And then they present the smoking gun, a piece of direct physical evidence linking the suspect to the scene. That blue color was the smoking gun. It transformed a fascinating hypothesis into the most powerful and compelling explanation we have for the entire story of 3I Atlas. It wasn't just a beautiful color, it was a confirmation. It was the final signature of its lost home, written in the language of quantum physics, and illuminated for the whole world to see. Our investigation has come to an end. We have followed the traveler's footprints, and we have found its home. Not a specific address on the cosmic map, but a type of home, an environment that we now understand much better. But the story of 3I Atlas is just one story, and the universe has billions of other stories waiting to be told. The chemical legacy of Atlas has opened a new door. It has given us a new tool to study future visitors. Now, when a new interstellar object is discovered, one of the first questions scientists will ask is, what color is it? Because they know that within that color may lie the answer to the biggest question of all. Where did you come from? The search for other lost homes has only just begun. The investigation into the lost home of 3I Atlas has reached a compelling conclusion. A story woven from orbital clues and chemical signatures, all pointing to a cradle under the light of a red sun. But the story of Atlas, as special as it is not unique. It is just one chapter in a book with billions of chapters. To truly understand our traveler's place in the cosmos, we must take one final step back. We must look at the entire Milky Way, not as a collection of stars, but as a sea of exiles. Chapter 8. Other Lost Homes and Conclusion. The process of dynamical instability, the migration of gas giants, and the gravitational slingshot effect were not rare events that only happened in the homeland of Atlas. Scientists believe this is an almost mandatory phase in the evolution of most planetary systems, including our own. In their chaotic early lives, every single star system in the Milky Way acts as an efficient launcher of comets and asteroids. Computer simulations estimate that for every one comet remaining in a star's Oort cloud, there could be tens or even hundreds of other comets that were completely ejected from the system. Now let's scale that up to an unimaginable degree. Our Milky Way galaxy has some 200 to 400 billion stars. If we assume that a large fraction of those also form planetary systems and comet belts, and also experience a similar phase of instability, then the number of interstellar objects of exiles wandering the galaxy is an astronomical number in the truest sense. Recent estimates suggest there could be up to 10 to the 25th power, that is 10 quadrillion comet-like objects drifting in the Milky Way. The space between the stars is not empty. It is a sea of exiles. Three-Eye Atlas was not a lonely traveler in the sense that it was the only one. It was only lonely in the vastness of the distance. In fact, it is a member of a huge population and invisible nation of homeless objects. A civilization of icebergs. At any given moment, scientists estimate there could be thousands of interstellar objects the size of Oumuamua or Atlas passing within the orbit of Earth. We just don't see them because they are too small, too faint, and move too fast. Oumuamua, Borisov, and Atlas were not miraculous rare events. They were just the first ones we had the technology to detect. They are the first drops of a coming rain. This completely changes our perspective of the Milky Way. The universe is not a collection of isolated island star systems separated by an empty ocean. It is an interconnected ecosystem, a global network constantly exchanging material. Fragments from our system, comets ejected by Jupiter billions of years ago, may be traveling to other stars, and fragments from other stars like Three-Eye Atlas are traveling here. Every star system is exhaling its own debris into the common space. Three-Eye Atlas was not just a visitor, it was proof of that connection. It was an ambassador, albeit an unwilling one, from another nation in our galactic federation. And it is in this sea of exiles that one of the most fascinating and profound ideas in science finds a potential transport mechanism. Amo. We have pictured a Milky Way that is not empty, but a bustling sea of icy travelers, fragments of lost worlds constantly moving between the stars. The existence of this sea of exiles is not just a curious astronomical fact. It provides a mechanism, a galaxy-wide transport system for one of the most profound and intriguing ideas about the origin of life. That idea is called panspermia, and these exiled travelers may be the sowers of the seeds. Panspermia, a word from Greek meaning seeds everywhere, is the hypothesis that life exists throughout the universe and is distributed by objects like comets, asteroids, and cosmic dust. There are various versions of this hypothesis. The strongest version suggests that actual microorganisms could survive an interstellar journey inside a rock, but a softer and more evidence-based version called lithopanspermia or chemical panspermia suggests that it's not life itself, but the building blocks of life that are transported. Those building blocks are the complex organic molecules, amino acids, the units that make up proteins, nucleobases, the letters that make up DNA and RNA, lipids, the things that make up cell membranes. This hypothesis suggests that life did not necessarily have to start from scratch on Earth from a simple primordial soup. Instead, the early Earth, a young and barren planet, was constantly being seeded by a rain of comets and asteroids. And these visitors brought with them complex organic molecules created elsewhere in the universe, providing a chemical starter kit for life to emerge. We have strong evidence for this hypothesis right here in our solar system. Scientists have found amino acids and other organic molecules inside meteorites that have fallen to Earth like the Murchison meteorite. Spacecraft like Stardust and Rosetta have also confirmed the presence of complex organic compounds in our own comets. And this is where the story of 3I Atlas and the Sea of Exiles becomes critically important. If only the comets in our solar system carried these building blocks, it would just be a local phenomenon. But 3I Atlas, with its brilliant carbon signature, has demonstrated that comets from other star systems are also extremely rich in organic compounds. It shows that the factory for producing the precursors of life doesn't just operate here, it operates everywhere. Now combine that with the Sea of Exiles, we have quadrillions of potential delivery vehicles, each supercharged with organic molecules. They are constantly moving between the billions of star systems in the galaxy. The Milky Way is not just a place of material exchange. It is a place of biological potential exchange. Each star system is not an isolated chemical laboratory. They are all part of a huge ingredient-sharing network. Could these exiled travelers be the chemical sowers of life across the galaxy? It's very possible. Perhaps the very carbon molecules that make up life on Earth were not born in the solar system. Perhaps they were formed in a distant red dwarf cradle billions of years ago. Perhaps they traveled through interstellar space inside an iceberg, just like 3I Atlas. And perhaps that iceberg crashed into the early Earth, releasing its chemical legacy into our oceans. From this perspective, we are all children of the stars in a very direct way. We are the descendants of exiles. We have come a long way. From a faint point of light on a telescope screen, a single clue, we began a grand investigation. We followed the footprints of 3I Atlas back through time. We journeyed with our science-guided imagination to a lost home under the light of a red sun. We explored a world of eternal sunsets, of locked planets, and of photosynthetic gardens that might be the color of the night. We witnessed the memory of the traveler's birth, a creation from the chaotic dance of ice and dust in an icy nursery, a place blessed with an organically rich chemistry. We have felt the drama of the chaotic dance of planets and the irreversible moment of ejection when a gravitational slingshot set it on a one-way path into the unknown. And finally, we understood. We understood why, after billions of years of silence, when it visited us, it sang a brilliant blue song. A song of its carbon legacy, activated by the light of a strange sun. A story has come full circle. The story of the lost home of 3I Atlas is not just an interesting scientific exercise. It is a testament to the power of human curiosity. Our ability from a few faint photons of light to reconstruct the history of a distant world is one of the most incredible achievements of science. It is also a reminder of our deep connection to the cosmos. We are not separate observers. We are part of the story. The fragments of other lost homes travelers like Atlas may have sown the first chemical seeds on our planet, contributing to the story of life itself. Their legacy flows in our veins. Each interstellar visitor is a messenger carrying a piece of a larger puzzle. Oumuamua brought the question. Borisov brought the reassurance. And Atlas brought the depth. Together, They show us a Milky Way that is not a static place, but a living, breathing entity, constantly exchanging, constantly telling new stories. The search for other lost homes has only just begun. With the new generation of telescopes, we will soon be able to welcome tens, even hundreds of visitors like Atlas every year. Each of them will be a new book, a new opportunity to learn about the infinite diversity of the worlds out there. Thank you for joining Cosmic Drift on this journey of reconstruction. Thank you for taking the time to travel to a lost home and to find answers in a streak of blue light. Now, it is time to return. Let the images of the twilight sky, of the black forests, of the chaotic dance of planets slowly fade away. Hold on to just one single feeling, the feeling of finding a place, an understanding, a peace after a long journey. The journey to the comet's lost home now gives way to the feeling of peace and safety of sleep. Let your mind rest. I wish you a truly peaceful night and sweet dreams of the homes you have found.